So we've seen some of the most amazing stars in the universe. White dwarfs, the size of the Earth. Neutron stars, the size of a small city, but all the same mass as the Sun. But now let's move on to the most amazing of the stars, the idea of a black hole, a star even denser than a neutron star.
And this concept goes all the way back to at least the 18th century. Back then, some philosophers came up with the idea of dark stars. And the idea here was that you might have a star whose gravity was so strong that light couldn't escape of it. Back then, they thought of light as being like a ball. So here's my light particle, a photon if you like, and the idea was that the light would be shone, you have a brightly shining star surface, it would go up, but the gravity would be so intense, it would come back down again.
So it wouldn't have escape velocity.
No, it wouldn't have escape velocity, just like this ball doesn't have escape velocity. It comes back down again, so the photons would come up and come back down. So you'd have a star that, according to their idea, might look very much like a normal star if you were up close to it, but the light would never escape. The gravity was too intense, and so it would be invisible. And of course, that could mean billions of these stars around the galaxy. They could be looming and approaching us right now on their way to kill us. And we wouldn't know because the light can't get out.
So to understand this, we need to understand light a little better, because that ball is not really a very good example of how light really works.
Yes, and in fact, the true idea of black hole is altogether weirder than this. And so to understand that, we're going to have to talk about Einstein's theory of special relativity. That's what we're going to do for the next several videos. Now, the first clue from this came maybe in the next century, the 19th century, with the discovery of electromagnetic waves. Now, back in the early 19th century, people like Faraday had shown that there was electric fields and magnetic fields. And it was eventually realised that if you change an electric field, like you say, have a wire and you suddenly apply a voltage to it, there's a change in electric field, and that generates a magnetic field. It makes a compass twist. But likewise, if you change a magnetic field, like by taking a magnet and waving it around, that makes an electric field. That's how dynamos work. You whirl magnets around to make electric currents. But the idea was, towards the end of the 19th century, that Maxwell came up with, so if a changing electric field can produce a magnetic field, and a changing magnetic field can produce an electric field, then maybe we don't need wires and magnets at all. They can just go by themselves through space. You have a changing electric field that makes a magnetic field change, it makes an electric field change, that makes a magnetic field change, and the two of them could just keep wandering through space, supporting each other.
So once you start one of these things going, you just sort of get this thing going off, right?
Yeah, and no need for wires or magnets. It could just sustain itself. I did the calculation, and you get the wave that looked like this, with the two components at right angles to each other, and calculated the speed. So it depends on two constants that can be measured in the laboratory, the constants of the electrostatics and magnetic fields, and it came out with a velocity. And when they did the calculation, the velocity came out as 300,000 kilometers per second. Now, that's a curiously familiar number.
That is an interesting number. That sounds an awful lot like the speed of light.
Yeah, so this was an amazing breakthrough, that we had light and we had electric fields and things, and people didn't realise they had anything to do with each other. And what did magnets have to do with light? But what we found out is, in fact, actually they're the same thing. That an oscillating electric and magnetic field actually produces light, and it comes out with that speed. So this led to the whole understanding of light for the first time. It led to the discovery of radio waves, so it's probably one of the greatest technologically useful discoveries of all time, along with thermodynamics and steam engines. But there was a philosophical puzzle here, because here's the speed, and that speed is absolute. It doesn't say with respect to what or where it's launching from or anything. It's always the same speed.
So that's saying that if we think light is actually this electromagnetic waves, it's sort of saying you might expect light to always have the same speed, no matter what's going on in your life, and that can lead to some interesting problems.
Yeah, and the problems that leads to, we have to go back to Galileo to understand. Galileo came up with the idea, it's Galileo's theory of relativity, which in its own way was every bit as amazing as Einstein's theory, in fact even more so I would say. And the first idea is that, let's say we take Brian and put him in a box, soundproof, lightproof box that lets no forces through. You have all the physics equipment you like in there, you can do any experiment you like, but can you tell where you are?
So, for example, if I'm moving, then I might expect the ball that I drop inside my box to have a different trajectory if I'm moving? Well, no, not if the ball is moving with me.
Yep. So the curious thing is that not only can you not tell where you are, So you don't know whether your box is in Alpha Centauri or downtown Canberra, unless there's some force. You can open the window or feel the gravity coming in from outside. But if you're floating freely in space, you can't tell where you are, because the laws of physics are the same everywhere. So no experiment you do will give a different answer wherever you are. So you can't tell in any way without looking outside where you are, without looking something out that's relative. But worse than that, you also can't tell if you're moving. Now this was a big controversy back in Galileo's time. He was proposing that the Earth went round the Sun, so that when the Pope is sitting in his chair at St. Peter's, he's actually moving at an enormous speed, 30 kilometres a second round the Sun. And his opponents thought this was ridiculous. If you're moving at these enormous speeds, wouldn't you feel it? You get blown back or something. But Galileo pointed out, no. Actually, you can't feel motion. You can feel acceleration when you start moving. When you put your foot down on the accelerator, you can feel that. Yep. But if you're just moving at a steady speed, you can't tell. And he used the example of being on a rowing galley, one of the Venetian Navy fleet. You could be doing experiments in the cabin there. If it was rocking, that's acceleration. You could see that. But if it's just going nice and steadily on a smooth sea, you drop things, they appear to land at your feet. They don't suddenly fly off sideways, even though you're moving.
And we get this same feeling, throughout our lives. For example, if you've ever been able to look out the window of a plane, when suddenly the plane gets towed back, you often can't feel the acceleration. And all of a sudden you look outside and you realize that, wow, outside's moving. Or is it you moving? It's kind of hard to tell. And indeed, the whole idea of Galilean relativity is it doesn't really matter. Either is equally valid. And we use this type of idea, I guess, throughout our lives, and we sort of take it for granted. But you really can't tell what's fixed and what's not. It's only when you say the Earth is special that you sort of have that reference point.
Yes, because we think of the Earth as being stationary. I think that I'm just standing here not moving, but of course I'm on the Earth, which is spinning at 1,000 kilometres an hour at the altitude of Canberra, moving around the Sun at 30 kilometres a second. The Sun's moving around the galaxy at 200 kilometres a second. The galaxy is falling into the Virgo cluster. The Virgo cluster is falling into the Great Attractor. So what, if any of these things, constitutes rest? And Galileo's key insight is we don't know, but we don't care. Because any motion that's uniform, we can't tell the difference. We can't measure the difference. It makes no difference. So there is no such thing as a universal standard of rest. Motion is entirely relative, hence relativity. So, important concept, but as we'll see, that gets us into trouble.